So when you open Mercury, if you go to File, Open, you're going to open the CIF file. So the one you downloaded was 638.505. You click on it. It opens it up here. Now this model that we're looking at is referred to as a wireframe model. So if you want to make it look more realistic than just a bunch of lines, we're going to go up here to Display, Styles, and right now it's wireframe. But if we click, for example, ball and stick, now it treats these atoms as balls and the bonds as sticks. But a more realistic representation of the model is if we go and we click on ellipsoids. And so here now the atoms better illustrate how the thermal vibrations inside the atoms are. So usually we do ellipsoid display. So if you go to display in the top left-hand corner, go to styles, and you go to ellipsoids, it puts the ellipsoids there. And so you can notice that the atoms are different sizes due to the amount of thermal vibration those atoms have. So the more vibrations your atom has, the bigger the thermal ellipsoid is. So for example, atoms in, for example, a benzene ring is very constricting. So there's little vibration typically in a benzene ring. So those carbon atoms don't vibrate that much. But for example, if you have a methyl group, the methyl carbon tends to vibrate quite a bit, and that can lead to what we call disorder in the crystal structure. And so this is our asymmetric unit. So what you're looking at here is the smallest region of space needed to generate the entire unit cell. So from this region of space, we can generate all the different entities in this unit cell. So this asymmetric unit is one molecule. And since this is P212121, which is an orthorhombic space group, there's going to be 4 total entities in the unit cell. So if you notice the hydrogens are missing, if you want to add the hydrogens, you come down here to where it says show hydrogens. For some reason, this one, maybe they're not in the CIF file. Yeah, so for this example, they didn't put the hydrogens in the CIF file, so it doesn't show them. But typically you can turn on and off the hydrogens by under options, show the hydrogens. If we want to show the cell axes, now we have the unit cell, and this is the asymmetric unit. So from this molecule here, we're going to generate all the molecules that are in one unit cell. And then this unit cell, if you can imagine, if you have a Lego, in that Lego, you know, there's 6 dots on it, and then you have the same exact Lego gets replicated in 3 dimensions. And so if you want to generate the symmetry related units, if we click on the packing, so what I did is, right now it's asymmetric unit. If I click on the packing, it generates the 4 symmetry related molecules in this unit cell. So again, P212121, what that is, and we'll talk more about this later on in the course, but 2 sub 1 is a screw axis. So if you think of a screw axis, if you if you stand up, you rotate 180 degrees, and then you shift to the left or the right, say 1 unit, that's a screw axis. So what this molecule is doing is here, this molecule is rotating 180 degrees, which puts it over here, and then it shifts down and you form this molecule. And then if you do a screw axis on this, it rotates, shifts up, and that's how we generate all of these molecules in the unit cells by doing what's called the symmetry operations. And I'll show you just in a second how to get these symmetry operations for this space group. So this is one thing you're going to have to do in your Mercury assignment is you're going to generate a picture just like this of all the symmetry equivalent entities in the unit cell. But you're also going to have to show the different types of symmetry elements. And so once you have this picture here, if we go up to display and we go up to symmetry elements, and here it shows you all the different types of symmetry elements we can have. Now for this particular unit cell, we're not going to observe anything but, where is it? Show screw axes with arrows. So when I click OK, what you're seeing is you're seeing a screw axis parallel to the A axis on the unit cell. You're seeing a screw axis, if I rotate it and we look down, for example, A now, if we're looking down the A axis, there's a screw axis parallel to the A axis. There's a screw axis parallel to the B axis. And then lastly, well, maybe that's the C axis, yeah. And that's screw axis parallel to the C axis. So these green lines with these arrows on it represent screw axes. And there are 3 different types of screw axes that are used to generate all of the entities in this unit cell. So we start with the asymmetric unit. We do a screw axis parallel to A, we get an entity, a molecule. We do a screw axis parallel to B, we get an entity, our molecule. And then we do the last one parallel to C, we get the last one of the entity. So since there's 3 screw axes, and remember every space group has the identity as well. So the first molecule shown has the what we call the identity symmetry, which is it has no symmetry, a 360-degree rotation, just like you learn in point groups. And so if you want to see these actual symmetry operators, we can go to display, more information, and if you go down to symmetry operators list, this shows you the different symmetry operators for your space group. And it's the second column that you'll need to record in your table. So this here, these are the 4 symmetry operators for P212121. So different space groups have different sets of symmetry operators for them. But again, you go to display, you click on symmetry operator list, and it's this column here that you're going to include in the table for the Mercury assignment. And the information description is nice. It tells you this is the identity, screw axis, parallel to A, parallel to B, and parallel to C. And this is the only type of symmetry in this space group is a screw axis. And by the way, this is one of the 5 most common space groups for organic compounds, P212121. Very common space group that we encounter. To change the background screen or background display, if you right click on the background and go to display options, you can change the color of your background. So if you wanted it white, for example, now you can have it as a white background. If you don't like your selection, just go up to edit and undo. Oop, but it won't let me do that. So we'll just have to go back to display options and set it back to the previous color. There we go. So that's something you can play around with later. So now when you're ready, once you have your symmetry elements, and you want to save this, if you just go to File, and you can save it as a JPEG. So if you look at the drop-down menu of files you can save as, one of them is a JPEG, and it'll save this as a nice picture so that you can import it into your Mercury assignment. Now, some other things that are not required for the assignment, but just to show you the powerful tool Mercury is that we can see, let me get rid of these. Is we can see the packing of the crystal. So now if we go up here and we go to calculate packing, you can say, okay, plus a 5 along A, and we click OK. It's going to generate a packing diagram of this crystal structure. And I guess I didn't change anything. Let me go back. We do 2. So we'll do 2 unit cells in each direction. And now you have the packing of it. Now, if we want to view along a particular axis, we come down display. We want to view along the A axis. The packing looks like this. So if you hold your mouse and you hold the right button, you can zoom in and out of your picture. If you hold the left mouse button, you can rotate your diagram. So right mouse, you can zoom in and out. Left mouse, you can rotate. And the reason you would want to view along different axes is sometimes, especially if you have a hydrophilic portion and a hydrophobic portion, usually these will align in such a way that you'll have a channel of hydrophilic region and a channel of hydrophobic. So now if we go display, we want to view along the B axis. Don't worry about the stars. They're called reciprocal axes, but we'll talk about that later. So this is what it looks like down the B axis. And this is what it looks like down the C axis. So this is how you can get different views of your packing diagram. Again, to get the packing diagram, we go up to calculate. You go to packing, and don't do it too big. So I just went to 2 unit cells in each direction, or in just the positive direction, because if you do too much, it's going to take a very long time to update your packing diagram. So this is one example of using Mercury. Now we're going to switch to another example. So here you'll notice that in this asymmetric unit, we have 2 molecules. So this one's a little bit different. If you remember in the previous example we just did, there was 1 molecule in the asymmetric unit, and we had 4 molecules in the unit cell once we perform the symmetry operations for that space group. But this space group here, if you haven't noticed yet, if you look over here in the right hand side, this is PNA2 sub 1. And again, like we mentioned yesterday, P means primitive cell. And we'll talk more about the centering later on. And you can see, okay, well, we have a 2 sub 1 here. So there's going to be a screw axis because 2 sub 1 represents a screw axis. Now, both of these examples here are in the crystal system orthorhombic. And so what you can do, what you'll know about the crystal system of orthorhombic is that the first symmetry element is always along the A axis. The second symmetry element is always along the B axis. And the third symmetry element is always along the C axis. So that's why we had a 2 sub 1 parallel to A, 2 sub 1 parallel to B, 2 sub 1 parallel to C. Now again, PNA 2 sub 1, this is an orthorhombic space group. For orthorhombic, the crystal lattice parameter restrictions are this, just to kind of show you. A not equal to B, not equal to C, alpha equal to beta, equal to gamma, equals 90. Let me get a slash here. So for orthorhombic crystal system, the cell axes are all different and all the angles equal 90. So now with P and A 2 sub 1, again, we're going to have 4 symmetry operations. So of course, one of the symmetry operations is always the identity of the identity symmetry. And so if we want to see what the symmetry operations are, again, we go to display, more information, symmetry operator list. And so again, we have the identity, X, Y, Z. So these are the operators you need to record. A screw axis is, again, if you rotate maybe your body 180 degrees and translate in either to the left or to the right, that's a screw axis. So we're doing a rotation and then a translation. Now the other two is an in-glide, what we call in-glide perpendicular to A, and an an A-glide perpendicular to B. And so a glide plane is another type of symmetry where if you were to take your body and cut it in half, you would have a mirror image of your body. And if you took half your body and translated along the A direction, that would be or excuse me, not the A direction. You translate it along the BC plane, you get a glide perpendicular. Oh no, excuse me. You translate along the A, you get an A glide perpendicular to B. So the reflection is along the B axis, and then you translate along the A axis. So it's a translation after you do a reflection. So mirror plane. So cut your body in half and move it up the A axis. And for an in-glide, perpendicular to A, an in-glide means that you translate along every axis and you have a reflection in the A direction. And so the way you know which one you have a reflection, just to give you a little prequel, is, so here is X, Y, Z. When we have a screw axis, 2 of the coordinates become negative. So a screw axis parallel to C means that X and Y become negative. Now, when you have a glide perpendicular to B for a mirror plane, only one of the coordinates is negative. So you see here, the y goes from positive to negative. This means that the mirror plane is perpendicular to B. Whereas in the last one, the x is negative compared to the first operator. So this tells you that the mirror plane is perpendicular to A. So for a screw axis, two of the coordinates are going to become negative. For a mirror plane, only one of the coordinates becomes negative. Because for a screw axis, you're rotating about one axis. So that means two of the coordinates are going to be negative. For a mirror plane, you're reflecting in a plane. So a plane means that only one coordinate is going to go from positive to negative because you're reflecting in, for example, the AC plane. So that means the B value would be negative. So this is just how you can interpret these symmetry operators. So now if we want to draw the unit cell, and if the hydrogens look like they're going to be kind of messy and hard to help you illustrate, you can turn off the hydrogens like that. Yeah, so for the crystallographic axes ABC, A refers to the fractional coordinate for X, B refers to the fractional coordinate for Y, and C relates to the fractional coordinates for Z. And that's how you can relate ABC, X, Y, Z. So now we want to draw the symmetry related operators. So we want to show our cell axes. So here, this is going to be a very crowded unit cell because there are two molecules in the asymmetric unit. And we're going to do there's four symmetry operators. So there's going to be a total of 8 molecules in this unit cell. And that didn't look good. Let me go up here, display. I got to fix this. Because it's doing 2 unit cells instead of 1. There we go. There we go. So now if I want to display, look down the a-axis, this is what it looks like. So these molecules, or these are stacking or propagating along the a-axis, because we're looking down the a-axis, you see the molecules going down the a-axis. And we display along the b-axis. And so here, what you have is a very common motif, which is a hydrogen bonded dimer. So these are carboxylic groups. Let me turn on the hydrogens for you. And so what you're seeing here, if I can zoom in, is you're seeing a hydrogen bonded dimer. So this carboxylic group and this one hydrogen bond, and this is a very strong hydrogen bond that holds those two molecules together. And so if you wanted to know the distance between these two, you can come to calculate. Let's see, which one is it? Contacts. Let's see. Oh, here, under the pick mode, there's this one. Yeah, we go measure distance. And it's about 1.87 angstroms, and that's a very strong interaction. So this is the type of information you can obtain by looking at the crystal structure. So this is down the B axis. It was just a display down the C axis. It looks something like this. And so that hydrogen bonding is occurring along the A axis. So if I go back to the A axis, we're looking down the A axis. So that hydrogen bonding dimer is along the A axis. So now if we want to show the symmetry elements, we go to display, symmetry elements. Now here, we're going to have quite a few different types of symmetry elements. So if you have different symmetry elements, it's best to show one of them at a time. So what I'm going to do first is I'm going to show the screw axis and not the glide planes. So what we're looking at here is a screw axis parallel to C, because the green lines with the arrow represent screw axes. Now, if we want to look at the glide plane or the in glide perpendicular to A, we go back to display, symmetry elements, we turn off the screw axes, and we show the glide planes. And so now we're looking, if we look down the A axis, this is the glide plane with the A glide, the in glide perpendicular to A. So since it's perpendicular to A, it's orthogonal to the A axis. And if we look at the A glide perpendicular to B, so if we display down the B axis, now we're looking down the B axis, the A glide is perpendicular to B. So that's why it's orthogonal to our view here. If we look down the C axis, so now we're looking down the A axis, so we're looking parallel to the in glide perpendicular A. So it looks like a line now. So we've kind of rotated it at 90 degrees. And so when you have multiple symmetry operators, it's best to show one at a time when you're completing the assignment. And one last thing, let's just do a little packing here, see what we see. So this is down the A axis, the B axis, and then the C axis. So this is how you get different views of the packing diagram from the different axes.